All right, so when is it? There we go. So who am I? I'm one of the DuckDB core developer team. My background is a little eclectic. I originally was in math. That turned out to be a bad idea. And then thank you so much. I got into the software industry, spent a lot of my time doing speech synthesis and other kinds of digital signal processing. And eventually I wound up at Tableau, where I worked on connectivity and query generation, and eventually something called the Tableau Data Engine, which was a embedded column store. After 15 years, I left Tableau and tried to retire and failed. I spent so much time hacking on DuckDB that Hannes tracked me down and asked me to join the team. And what I do there is ordered data analytics, specifically the window operators and things like temporal joins and grubbier stuff like temporal data processing, time zones, things like that. So what is DuckDB? Well, here's a pile of buzzwords. And we'll get through to all of them. It's open source, vectorized, in-process analytic database engine. And why is it called DuckDB? Well, Hannes, one of the founders, lives on a boat in Amsterdam, and he decided he wanted a pet. And having a cat seemed like a bad idea. So he adopted this duck named Wilbur. And this photo is actually from The Guardian, who went around Europe at one point and collected people who had weird pets. So he wanted. So what is DuckDB? Well, there's many ways of slicing up what kinds of databases there are in the world, and this is one way of slicing us up. Traditionally, you've had client-server databases, and they were split into transactional and analytic, or OLTP and OLAP. And examples of those are Postgres and ClickHouse. I'm sticking to open source projects here. But there was also this category of in-process databases, which were exemplified by SQLite. And I don't know if you know this, but SQLite is probably the most installed database on the planet. It's in everything. It's in your phone. It's in airplanes. It's really quite spectacular. But there was this hole here for doing analytic processing in process. And that is where DuckDB fits into the world. When they started this project, they had a few design goals. They wanted it to be really simple to install because the people who are using it didn't have the time to mess around with. They were already frustrated by having to set up servers, and they were using non-database tools to do database operations over at CWI in the Netherlands. And so they wanted something that had no dependencies, had to be in process, so there's no server to set up. They didn't want them to have to configure it. I mean, there are people who write papers on how to do automatic tuning of databases, right? They didn't want to have anything to do with that. And they wanted to make the SQL language friendlier because it's a little unforgiving at times. And we've pretty much succeeded on these things. On the off chance that nobody knows what vectorized columnar processing is, there's sort of three models for doing row-oriented processing. The old one is tuple at a time, and SQLite actually does this. You get very low RAM use, and you get a lot of code overhead because everything requires, to jump around for procedure calls. At the other extreme, you have column at a time processing, and a good example of this is Monet. And this is great because you've got all the prefetching as you scan down each column, but stuff winds up getting kicked out of the caches. This is also a problem with tools like pandas, which are also basically column at a time processors. DuckDB uses something called vector at a time processing, which is a sweet spot for hardware. Because you deal with about, in our case, 2K rows at a time. That all stays in the cache. You get everything done, and then you move on to the next one. You still get a lot of prefetching, but you don't have to worry about stuff winding up on disk and then you need it again. So that's basically what is DuckDB. But why? Why do we need another database? And my college roommate used to say this all the time back in the 80s. So Well, part of what happened in the last 10 or 15 years is that hardware went through a sort of state change, and Moore's law was over. So we weren't able to make CPUs any faster. So we started making a lot more of them, right? And memory continues to be expensive, but we started getting solid state disks, and those are a lot faster than traditional spinning media. So now we have these machines like this one, which have a lot of cores and a solid state drive. But at the same time this was going on, people were building libraries like pandas, which are very convenient to use inside Python, but they don't scale to the kinds of hardware we now have. And I'm not, I'm picking on pandas because I don't want to go through all of them. But you wind up with many copies of the data. Python doesn't run parallel processing very well. A lot of these, algorithms inside of pandas are not the kinds of things that we in the database community have been working on for 50 years. There's very little compression. They really don't do out of memory operation. So you're limited to how much data you can process. And they don't have an optimizer. If you do a series of steps in pandas, it doesn't look at it and say, well, actually, you should move this filter over here. That's a problem. And all of these cores are something pandas can't do because it's pretty much single-threaded like most things inside of Python, which limits its scalability. And if you start comparing it to what we can do, it gets a lot slower. Now, people knew that pandas was a problem. So the solution until recently was, well, let's throw it at Spark if it's too big for pandas. We can automatically distribute the computation onto many machines and scale out. And this all sounds great, right? Well, the problem is that scale out only works well for certain algorithms, especially ones that are embarrassingly parallel and IO heavy. Anything else, you start to run into problems with communication delays. Doing joins, you've got to move stuff all over the place. Large aggregations, which processor has which bucket on it, and just lots of different things. And Spark, even when it works, it's a little clunky. You have all this communication, you got to worry about scheduling, all the network requests go everywhere. And the minimum latency for loading something into Spark, even though a few K, is measured in seconds. And one of the things I picked up at Tableau was if you're trying to do interactive work, usually you want to keep it below 200 milliseconds for people's, before people notice something is going on. And there's also a bunch of costs with using Spark. It's kind of hard to develop for because everything's happening somewhere else. There's all this high latency I've talked about. It's also kind of expensive because you have to get a cluster, rent it, pay for it. And it also, that burns a fair amount of carbon if you're also, you have another hat which is working on climate issues. So even in the best case, it's not really very optimal for this sort of stuff. So these were the kinds of problems the DuckDB was set up to try and deal with. And there's a whole bunch of stuff, and I'm going to try and just keep it to a few things. So first of all, beyond memory. Because we're built like a traditional database, we have paging. We can write data out to disk if it gets too big. And we try to work on not just slowly degrading. And actually, this is a thing that's a little different that Lawrence, our sort guy, has been working on. Is often there's this cliff when you suddenly have to page out to disk. All of a sudden, all your data structures change and you have to rewrite everything. We've been working on having data structures that you can start paging immediately so that you don't have this kind of degradation. And we've gone pretty well on some of these beyond memory operators. It's still a work in progress. There's still a few corners. But I finally got around to windowing last winter. So we're getting there. The other thing we can do, yeah.
I had a question for the previous slide.
Yeah.
I actually can't quite tell if this figure shows a cliff or not.
That's one of, no, that's just where he started, was at 10. And then it just kept going. And then, yeah, by the time you crank it down to 1 GB, this is one of his sorting queries. I was thinking I should go find out which one it was, but this slide's been in our presentations for a couple of years.
You can kind of see the need in the curve round 4.
Um,
Often the system should look for where's the need in the curve. Right, and then it's not, I mean, it's not exactly right, but you can kind of.
yeah, I mean, eventually you will fail, right? I think is the point. But we can keep going. But as you down here, it gets a little worse, and then finally you sort of run into a wall. I think is what he was trying to get at. This one's a little straighter. So this is parallelization, and this is another thing we can do, having a traditional database scheduler. We have parallel, every operator is built to be parallel. And we can then do load balancing, we can schedule, we can keep threads independent, and so things can scale up pretty well. This one actually is labeled. This is a EPCH query. So those are two things we can provide for to deal with these hardware issues. But there are other things that are very useful for our audience. Okay? And data connectivity is one of them. When I got to Tableau, I found that they were talking to a couple of databases. Almost all of them were Microsoft products. And this perturbed me because at the time, this was like 2004, the most popular database in the world was MySQL. So I sat down and rewrote the connectivity layer to be able to talk to not only MySQL, but to be extensible so that we could talk to anything. And by the time I left, we were talking to 50 different vendors. Are there too many databases in the world? So being able to import data is crucial. And the reason I have a picture of my solar panels up here is to give another example of this, which I have solar panels, I have a switch, I have a battery, I have the grid, I have the house, and the house has a charger for my car. And because these things all speak 110 at 60 hertz in the middle, I can use the solar panels to charge my car. Right? So just being able to move data around through a common representation is very powerful. And we have a lot of connectors, and I've only listed 5 here, but the number keeps growing. And the reason it keeps growing is because DuckDB is extensible. And so if we have a feature that's missing, you can write your own and then maybe ask us to put it in there. And this starts with simple things like scalar functions. Our time and space stuff is all run through extensions. And table functions. So we have a Postgres scanner and SQLite and a whole bunch more. And I've downloaded a bunch. These are the officially supported ones. There's also an entire community repository of people who just write extensions. And one of the things to know about the table functions is that we don't prioritize our own access to our own database file. Okay, we use the same APIs as everyone else. And this keeps us honest and keeps things performant for everybody. But it also means that DuckDB is a great thing to use as a research platform, okay? Because we don't just have plugins for scalars and tables. You can hook into the parser, you can hook into the optimizer, you can write your own operators, you can write your own storage layers, and there's a couple of other things. I was looking around the code and seeing, oh, there's more stuff. So, and the reason I've highlighted optimizer is right now I'm trying to write my first one to do an optimization that I'm not sure is a good idea for certain kinds of windowing functions based on a paper from the LDB last year. I kind of wish the guy had used that instead of writing some Java that took a query and then parsed it and took it apart. It's kind of horrible. But as a research platform, there are people already doing this. No, that should be 2024, sorry. This was, I believe, presented last year at VLDB as well, a join reordering algorithm. And there's a podcast called Disseminate, which has done a mini series recently on using DuckDB in research. So I hope this encourages people to have a go at using us for that. So that's what we can offer. So now let's wade into what I do. One of the big things about being inside of Python and working with data frames and working with people who are not database people is that they all have a mental model of data that is physical. It's ordered. Okay, so data frames have natural orderings. CSV files have natural orderings. Parquet files have natural orderings. And they expect us to be able to handle these kinds of orderings. And not only that, they expect to be able to ask questions about their data that are ordered because that's what they're used to. Okay. So we actually have one of the best sorting algorithms on the planet. It's a radix sort that's Lawrence put together a couple of years ago, and he's not done. He's making it even better. And like all good database systems, this isn't just off in a corner in the order operator. It's generally available to the system, and I use it in a couple of my operators as well. And it does all of this great stuff like spilling to disk. And this is a chart. This is a couple of years old when he first did it, but you can sort of see that we're squeaking ahead of some of these tools, especially ClickUp. So what kind of things can we use this for? Well, one that I find a lot of databases don't do very well is range joins. And this is where you have an inequality, right? And the use cases for this are like you want to join two tables together where you have overlapping ranges. And often the ranges are disjoint, so you'll only match one row. And if you've done temporal analytics, so will be like a joint state table. And the example here is something I made up when I was heavily into Battlestar Galactica. And you've got when people are flying and when battles happen, and these are not the same thing. And then you want to give them combat pay. Yeah, right. Like they had that in the colonies. But you then want to intersect these ranges and produce what's called a joint state table. And the joint state is for, say, Starbuck, followed the colonies, was fighting in this range here. Okay. And we picked up two join algorithms for this. One was from a couple of years ago. I don't see people using it. I'm not sure why, because it really seems to me to be the best general purpose algorithm I've seen. It's called IE join. And there are faster ones, but they all require metadata that most people don't have. So, and this one can handle two inequalities pretty well, and especially if you are in the very common case of there's only one matching row. You also have one for a single inequality, which is a sort of modified merge join that Mark came up with. Maybe this is more general. I've only seen him do it, where you sort the build side, and then every vector that comes in on the probe side, you sort that, and then you do a little merge join right there. And that one's pretty effective. So that's range joins. Then there's this thing called an as-of join. And people who are doing a lot of stuff with like stock data, so they really like this because you have a list of prices for some equities, and then you have times you want to check what the value of the portfolio was, but those times might not match up from when the trades happened in the market. So you have this thing called an as of join, which says, as of this point, what was the value of this measurement? And so it joins these two time series. It says time series, but we've generalized it for any type. And it's not just stocks. I hate the example of always being stocks that people are using this for. But again, because I do energy stuff, utility time of use tariffs is also a nice, great way to use it. And then there's this thing called event tables. If you have a log, you have a timestamp when things happen. That is effectively an event table. And you want to know, at this point in time, what was the last what was the last time this user tried to do anything? So you want to look back. And that's another use for as of joins. Yeah.
Just to make sure I understand correctly, this is an as of join is the closest timestamp, not the closest prior timestamp.
It's the closest prior. Yeah,
So you-
and actually you can, we've got all four inequalities in there. So you can do, and I have a blog post somewhere which explains the semantics of each of the different inequalities. And so, oh, so we have a blog full of all kinds of bizarre information, including things like this, if you want to go digging deeper into any of it. And the last one of the joins, if you're sitting there with two data frames that are the same size and you want to iterate through them together, this is trivial to do in Python, right? It's really difficult to do it in SQL. And so we've added this thing called a positional join, and you can have two or more tables, and we just scan down all of them in parallel and just horizontally fuse them together. So I mean, you don't have to worry about doing a hash join on the row IDs or anything like that. It just streams right through. Yeah.
Does this mean that, because when I think about like why traditional databases didn't do this, is they didn't want to make a promise to the user about the ordering of the rows in the database.
Yeah, well,
Like, so how does DuckDB communicate that to the user, and what is the contract there?
well, if you specifically have to request a positional join, it's a keyword, right? And if you do that, then we do it single threaded, and we do have a way of physically reading tables in a particular order, and there is metadata that propagates through the operators saying, you know, which block is this, which row group is this, and so we keep it all straight that way.
But I guess as a user, how do I like know what the order of the tables was before I asked for the join? Do I need to do it?
You're asking this question as a database person. What I'm trying to get at here is that most of our users are not database people.
Yeah.
They're used to having data frames that have a particular order. They've got an index column, right? Or they're looking at their CSV data on disk or something like in their spreadsheet or something. So they already know what the order is, and when we don't know what the order is, they get upset.
Okay.
That's
so
the way.
order is the order that they gave it to you in.
Yes, it's
Okay,
the
that's-
physical order. Yeah.
So by extension, every time I run a select star, it's the order I get when I run a select star.
You can't. We try not to do it that all the time. Okay, but if you have a positional join, or I'm going to get to a variant of windowing that we do, where people are like, "No, I just want to, add row numbers." We do try and preserve the initial ordering, and we actually have pragmas to like turn that on and off. So, which I wasn't going to go into.
So then one question.
Yeah.
So to do this, do you actually add like some kind of indicator of the order when the data is first ingested? Or do you just rely on the ordering that like when you ingest it, you're going to preserve the order when you store the data, and then when people do positional sorting,
Yeah.
that order from the stored data?
Yeah, there's both. So if you're scanning a CSV or a Parquet file, then there is a physical order mostly, unless you're doing,
So then you just preserve it.
we just preserve it. But when we insert data, we also preserve notations about that. Okay, so we can then go through and say, hey, pull this in this
So you
order.
annotate it, so then you can use it.
Yeah,
for someone's order.
All right, yes.
It gets more complicated. So what if my data is not read from disk, but it is a join of two tables?
Well, then we wouldn't let you do it.
I can only do this on two base tables.
Yeah, or something physical. We have talked about finding ways to parallelize it, but haven't gotten around to that yet. So like making sure that you read different groups, but yeah.
It's not compositional, this language. I can't plug in, instead of a table, I can't plug in an expression.
Probably not. Although we are talking about keeping track of ordering metadata and then leveraging that. So like a window operator might do something like that, or an order by might do that, in which case you would be able to leverage that. But yeah, no, this is because people who don't know these things as well as you do want it. So we have carved out little areas where it works for them. But yeah, sometimes we have to explain to people, no, you can't do that. And yeah, but we try to do it as much as we can because we're trying to be nice to our users. So I keep talking about windowing. So let's wade into windowing for a bit. I don't know how familiar everyone is, so I'm going to very quickly go through what windowing is. The original SQL model, you had ordinary calculations that produce a new attribute from a single row. And this is really great because you can stream it, you can parallelize it, you can do all kinds of things with it, and you've just got this little thing where you're doing your computation. But people were used to spreadsheets, and in the 1990s, they started asking for multi-row calculations. You want to produce a new attribute from adjacent rows. And because we have sets, we don't have any meaning for this, because they're unordered. So we need boundaries, we need ordering, and we need distance. And so the SQL committee came up with this over clause, and you break the data up into independent blocks, partitions, using the partition by clause. You sort each one, and then you can express the distance in 3 different ways there. Rows is just literally rows. Range is a distance relative to the single ordering column, which has to support arithmetic. And then groups is peers, so chunks of equal ordering groups. So that's just basically how windowing is described. And the way this gets implemented in a database system is, of course, with an operator or operators in our case. The traditional way of doing this, when it first came out, was you materialize everything, you sort everything, and you sort it on both the partitioning and ordering keys. So you just get this huge sorted pile of rows. And then you look at the functions you want to do, and then you group them up by sorting spec, and then if you have different partitioning, different ordering, you then make another one, and you just chunk them all together like that. Yes?
Just to make sure I understand semantics correctly, the window is only within one partition.
Yes.
If I'm at the very bottom of the partition, I only look up and never into the next
one. Yes, exactly. So this is the way people used to do it. About 10 years ago, there was a paper talking about, well, perhaps a better way to do this is to take the partition keys and hash on them. So you get smaller buckets that you don't have to sort as much. And their paper suggested 1024, I think we're using 2048. But it reduces the sorting size, but now you can have hash collisions, so you still have to do a full sort, but you're doing a full sort on, 1,000 times less data, which is significant a lot of the time. Now, when you have those kinds of hash groupings, it's very tempting, and I was tempted by this, forgive me, I have sinned, to just say, okay, well, we'll just stick each one on a separate thread. And then they can all work independently. They can build any acceleration structures without worrying about locking. And this is great until you run into a situation where you have a lot of skew. Okay, and then you've got one thread that's sitting there crunching this humongous partition, and then all the other ones are just sitting there twiddling their thumbs. So last fall, I went and switched this to doing one partition at a time. And you can now use all threads. You start with the largest one and then just start filling in. This keeps the cores all busy. The downside is that you have to make sure that any acceleration structures you want to build can be built in parallel. As it turns out, all the ones we were using could be built in parallel, but I had to go make sure that they were being built in parallel. So this was an important change. The other downside of doing this is that before, if you have one partition per thread, then you can start propagating some metadata down that pipeline, which says, okay, the partition columns are only these guys, right? And you've got a full sort on the entire partition. If you start doing this, then the partition is scattered across all the cores, and you lose the ability to possibly reuse that metadata. But we weren't reusing it again anyway. And what we may end up doing is having some configuration which says, okay, if this is really important, maybe we should go back to the skewed situation. But that's sort of future work. So this is the basic physical window operator. But a couple of years ago, Lawrence, who I keep mentioning, he's a lot smarter than I am, said, hey, maybe this a way we could do some streaming windowing. And this gets back to how do we communicate to people that there is, we want them to use the physical ordering here. And if you have an over clause with no partition and no ordering, it's supposed to mean the entire data sets and then there's no framing at all. You just compute one aggregate. We decided, and in fact, I think some databases don't even let you say that. So we decided to overload this. And if you do that, we will try to just stream the windowing functions on a single thread. And the framing will then be running total type. So far, what have we got so far? Right? And this turns out to be more useful than you might think. A lot of people run queries like this, especially a very common thing people like to do with SQL and data frames and some of these other formats is they get very insecure when they don't have row numbers. So they like to they're like, oh, I got a window function. I can just add row number. The fact that you have to then materialize the entire data set and then add this number to it, that's not there in their minds. So we put this in there so that we could start doing things like that. And it turns out there's a bunch of other places or things you can do that within this model. And I keep thinking of new ones. And recently I've said, oh, we could put filter in there. You just don't aggregate that value. You can put distinct in there. We just keep a hash table. And then lead and lag is another good one. You just keep a little buffer as you're streaming. And we made it the size of one vector. But it turns out that almost every time someone does lead or lag, the value is 1. So this works really well. So, and the last piece is, how do we do planning for windowing? Do we stream? Do we materialize? So we start looking at all of the functions, and if there are some streaming ones, we pull those out first because we don't want to disturb the order, right? And then the remaining ones, we put everything if everything has the same partition, we throw it together. But then the sort keys, you can do this thing where sometimes one might have have a prefix of the sort. You say, well, how often does that happen? Actually, a very common one, which we have another optimization for, I'll get to in a moment, is that that there are no sort keys. And what that means in windowing is you just have the same value for every row. So by doing this, we get to combine, you want to compare the moving average with the average of the entire partition. We can compute both at the same time. Now, there's a paper for how you do all of this optimally. It's NP hard, so they got a good paper out of it. But I've never seen more than about 5 of these things, and I haven't bought 5 window functions at a time. And I haven't bothered to go and do their heuristic approach to that. So that's the operators and how they're structured. And the other big thing that we've done a lot of work on is computing aggregation functions. For windowing, there's a bunch of regular functions like row number, but then any aggregate you're supposed to be able to do windowing with. And this can be a bit of a bear for some of them. And you really want to take the time to figure out ways to make this more efficient. I mean, if you think about the simplest way you could do a windowed aggregate, you say, here's my row, here are all the values, let's just add them up or whatever, and stick that value there. Move on to the next row, start over. Here's all the values. But often frames are very close to each other. So you've thrown away a whole bunch of useful information. So we've come up with this thing called aggregation accelerators. And there's three big ones I'm going to talk about here. We also do have an implementation of the naive one, which is very useful for checking whether these complicated algorithms actually do the right thing. And if you turn off the optimizer, we will do that. It'll be slow, but it's almost certainly correct. So the first one is what I call single value or constant. This is where the case I mentioned a little earlier, where you want to get the average across the entire partition, okay, and then compare it to moving averages, say. And the way you specify that is you don't have an order by clause. Now this will produce only one value per partition. Now we could go and compute it for each row, but that's that's really slow. So we detect it and then only compute it once, and then we copy it to all the rows. Now there's a very common case in a vectorized engine where your vector is a constant, and this is something we support. And so instead of producing 2,000 values per chunk, we produce one value. And I ran into when I first did this, I wasn't setting the constant vector thing, and somebody complained that they were building some several thousand element long list using the list aggregator, and then it was just running out of memory. And if I mark it as a constant vector, then it all runs in like 50K or something. So, but the workhorse of aggregation is this clever idea I gave from Victor called segment trees. And the idea is you just build a tree where you do partial aggregations all the way up. And you can, in fact, build this in parallel, which is great. And so if you want to get the sum, say, of those, 7 elements there, you actually only need to add 3 things up. And so you just build this data structure once, and then all threads can then read it. They can do any kind of range they want. And this can handle any aggregate, because the only operations you need are, creating a state, merging a state, and finalizing a state. And the merging a state is something you already have in order to support parallelism. So all of our aggregates can be handled by this. But there are some things it can't do, like if you want to have a sum distinct, you can't use this because you don't know where the distinct values are, and they're mushed all around in the tree. Yeah.
So just to make sure I'm like grabbing kind of how this all works. So how these would be used is per partition, you'd like scan the data once to build the segment tree.
Yeah.
And then you go back through and like do the windows with the tree itself.
Yes.
Okay, cool.
Yeah. So there's a build phase. It's like joins. There's a build phase and then a compute phase.
Okay, nice.
But there are limitations. You can't handle distinct. And another one that's a problem is if you have a holistic aggregate like a quantile median, each level of the tree will have another complete copy of the data, so it'll just explode. So you don't want to do that. And the higher level observation here is that the window has a frame order, but the aggregate wants it to be in a different order. So how do you do 2 different orders at the same time? And Adrian came up with this thing where Adrian is not a duck and neither is Victor. They're German database people. And you build this tree that allows you to do the sorting in two dimensions. There are also data structures which will do n dimensions. I haven't waded into those. But if you do this, if you want to do a distinct, you really want to just have it in the order of the values, and every time there's a duplicate, you skip it. And this is what this data structure allows you to do. It also solves the problem of these holistic aggregates like quantile and moving absolute deviation. Because to do a quantile, you want it in a different order from what the window is in, and this allows you to do this. And fortunately, you can build this and query it in parallel again. So building all these acceleration structures is still parallel. And last of all, though, sometimes none of these things work and you just want to hand it off to the aggregate. You want to throw up your hands. And holistic aggregates are a lot like this. Quantile, for example, we actually don't use we don't use the merge sort tree out in the operator. We just hand it off to it to work with it itself. So internally, we have this custom window APIs. And so you can create an initial data structure, and then you can, on each thread, you'll get, here's all the input values. You can keep your own persistent local state. Here's the old frame, here's the new frame, here's the row you're at. You know, have fun. Tell us what the answer is. It turns out you can do some wacky things with this. I'll get to that in a second. So that's what we've done so far, and we keep thinking of more things to do, which is fun. One of them is the optimizer, and I got a couple of big things here. One is when we decide how many hash bins to make, that's based on cardinality estimates. We can adapt, but it would be nice if we could get it right the first time so we don't have to rehash. Python users love some anti-patterns, which are very common in in Python. And this is my favorite. They want to pick out for each user, they want to pick out the last time they came to your website. So this is what they do. They create a window function, partitioned by the user ID, order by event time descending, and they compute the row number, and then they just take everywhere where the row number is 1. So they take the entire data set, break it up into pieces, sort it, and then pull out 1. And I'm sure everyone in the room knows that the way to do this is with this just a self-join on an aggregate. All right, so figuring out when this is happening. There was a paper at VLDB last year, which was talking about self-joins. I think he was protesting a bit much, but this is definitely a case that I'm currently looking at. And that, in fact, I'm using the plugin architecture to try and figure it out before I inflict it on the code base, assuming I can even get it to work. So that's one. I mentioned earlier, we really like to start propagating ordering as metadata through the execution tree. And so that's something we can then use in the planner to reduce sorting. If you have windows and you can reuse some of the sort, that determines the order in which you should execute them. You could also maybe even remove an order by clause if you know the data is already ordered that way, and so forth. And then there's this other thing. We have a web version that's kind of crazy WebASM version of DuckDB. You can actually run it in a browser. We cross-compile it to it. And the guy who did that had this other way of breaking up window functions into small micro operators. I don't think we'll do that, but if we had those tools, that's something that we might do in the planner. The last one here, motif detection. Match recognize was added after the original Windows specification, and it's designed to match patterns and things like, there's this thing that stock analysts like called a cup and handle. There's an example of it. And we've had talks here on visual query languages like Ketchins and Visage. And if you can sketch that, maybe you can translate into a pattern and have match recognize pull it out. And this is actually being worked on by one of Hannes's students. And the way they're doing it is they're doing horrible things with custom window functions. So another unexpected benefit of having that flexibility. So when this talk was originally requested, it was all about what is it like to work at DuckDB. So I hope I've given you some of that. But the last thing I can do, because I'm actually a consultant and I keep careful track of my hours, I made this viz of how do I spend my time? All right. And it's not the same number of hours every month, so I've normalized it. So I broke things down into features, bugs, and marketing. And if you're wondering what marketing is, this is marketing. But one of the things you should notice, because this is a mature project, as time goes on, the amount of time you spend on bugs keeps going up. It's a little exaggerated because I've been out of the country and only have my laptop, so I wasn't trying to do anything too complicated the last 2 months. But yeah, there's this trend. This is not to say we're not doing fun things, but yeah.
Maybe you should spend more time on the features then.
Yeah, well,
So what was that big thought in February?
that was a major release. Also, I was traveling then, so yeah. So that's how I spend my time and how you spend your time. If you have a work permit for the Netherlands, we are looking for a software engineer intern for the summer. So, and they have verbose versions of it, and I've just simplified it so you can get the bullets here. So please feel free to apply. I believe applications close on June 16th. But if you're an EU resident or you have Netherlands work permits, they cannot help you get it. They're not set up for that. You'll have to have that yourself. But yeah, they're looking for a summer intern over there. And when I push my slides up, these are all the references I've come up with. And I'm almost perfectly on time, which I was not expecting. So, questions?
So kind of very cool, work, very interesting, so